Good afternoon. Chemists will get started now. I hope everyone had a great weekend. Hope everyone had a great fall weekend. Fall weather is among us now. All right, thanks, guys. All right, we'll get started then. We left off talking about balancing equations and how to do that, and the whole idea is first we need to spend some time and identify the substances that we're working with trying to balance. That's tied to the identity of the substances that we are working with. So oftentimes subscripts here, remember our work in chapter 2 where we took all that time to identify things. Based upon the charges and ionic compounds or the naming scheme, that's where subscripts go, when we just identify stuff. So once you've identified everything, then we balance our atoms by only changing coefficients. So coefficients here are these big numbers out in front that just tell us how many of each water molecule, for example, there are. Because we already spent the time identifying via the subscripts that water is H2O. We don't want to balance this equation by adding like a 2 in front of oxygen and H2O. We don't want to do that because we've literally changed the identity of the substance. So coefficients to balance, subscripts to identify your substance. So let's do some examples here of balancing. Okay, so I have a picture here for you of some chemical reaction. A, those are the blue spheres, and then and let's say B, the element B are the red spheres. I don't know why I made it that way. Okay, so we need to identify what's going on here. So let's look at the before picture because it looks like this is what is depicting the reactants. So what is this guy? What is that? How should we depict that as a chemical symbol? B, yes. So just B, nothing else, no embellishments on it, it's just B. Yeah, it's just B because in this picture, it's just one atom in this case. So it's just a B atom. Because that differs with this molecule. How would we describe what this thing is? This is A subscript 2, yeah. So the subscript 2 is, I'm trying to tell you, hey, there are two A atoms bonded together to form this A2 molecule. This is not the same as saying 2 A atoms. That's different. 2 A atoms would signify 2 blue balls next to one another. So we don't want to say 2A, we want to say A subscript 2. So it looks like that's what the reactants are. Okay, so then how would we describe the product? So it looks like there's 4 of them here. Oh yeah, we didn't actually count up what's going on here. So how many A2 molecules do I have in this picture? 4. And then how many B atoms do I have? 4. Okay, great. Then we draw our arrow. Now let's figure out what that molecule is. What would we call that? BA2. Yep. Or if you said A2B, no big deal, same thing. Okay. All right. Whatever order that is. So in the after picture, it looks like there's 4 of them. All right. So 4, I'm going to go with BA2. All right. Check yourself. Is everything balanced here? How we have our coefficients? Yep. All right. So the coefficients is just talking about how many of each particle there is, and the subscripts relating to the identity of how that molecule is actually composed. So we want to get the balanced chemical equation for this. So this is balanced. So is this my full chemical formula? So is the answer A? I meant to put a 4. There you go. Yes. So okay, everything's balanced. So is the answer A? What's wrong with the answer A? It's not the simplest number. So yes, answer A, exactly what we have written, is in fact balanced, right? And does represent the chemical equation, chemical reaction that's happening. But it's not the simplest way we can express it. So what should be the answer? B. Yep, B. All right. Where I just divided all those coefficients by 4 because there is a simpler way to express this. So what kind of reaction is this? Oh, wait, I didn't get to that yet. Never mind. It's on the next slide. Okay, so here's an example where we went through identifying things, balancing those atoms to get the balanced chemical equation. So let's talk about the types of reactions that there are. All right, so there's 3 in this chapter that we'll go over, 2 in the next chapter. So in the corner, I have, what trait we're looking for when given a chemical equation. We can identify what kind of reaction it is, whether it has one kind of product or one kind of reactant, or a combustion reaction, which is a reaction with oxygen gas to produce CO2 and water. So for a combination reaction, we're combining stuff. We're taking more than one thing to make one kind of product. So that idea that you only have one kind of product present at the end, that's indicative of a combination reaction. Where our decomposition reaction is just the opposite. You start with one thing and it breaks down into many things. So decomposition reaction, look for one kind of reactant. And then the last one here in this chapter, combustion reaction, burning things. Combustion reactions were usually, at least in this class, burning hydrocarbons. So things with carbons, oxygen, carbon, hydrogen, sometimes oxygen, but we're burning it with oxygen gas that's, in our atmosphere. And our products are CO2 and water. In this case, usually both of those are gases. All right. So when I say let's combust something or do complete combustion, recognize that you need to add the oxygen, because in order to burn stuff, you need to fuel it with oxygen, and your products are CO2 and water. All right. And so I have strategies to balance all of these. So let's put our balancing skills to the test on the next examples. All right. And then just be patient. We'll look at these last types of reactions in the next chapter. Okay. So balancing reactions. The idea here is you need to identify first using subscripts where appropriate, then balance using coefficients, balance the atoms using coefficients. So this is the hardest part, reading and then writing the chemical formula. This is the hardest part. So aluminum metal reacts with chlorine gas to form a single ionic compound. All right, so let's just go through all of these substances and figure out what they are, how we would represent them with symbols. Aluminum metal, how do we write the symbol for that? Al. Can you be a little bit more specific? Remember all the components of a chemical reaction? Solid, very good. Yep, okay. Al. What about chlorine gas? Cl2. How do you know that chlorine gas is Cl2? It's one of the 7 diatomics. You just need to memorize them, right? Hydrogen gas, fluorine gas, hydrogen gas, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of those are diatomics. So when I say oxygen, you need to know it's O2. But if I say aluminum, that's not one of the 7 diatomics, so it's just Al solid. Okay, great. So these 2 things are reacting. So those are the reactants. Now the hardest part of this question is figuring out what the product is, because I don't tell you what it is. I just say it's an ionic compound. So if it's an ionic compound, it's formed from ions, right? What are the only sources of ions that this compound can be made out of? Aluminum and chlorine, that's it. So you need to figure out what kind of ionic compound is made from aluminum and chlorine. So this becomes a chapter 2 question, where it's, okay, when aluminum is in an ionic compound, what charge does it take on? +3. So this is not part, so these 2 are part of the chemical equation. We're combining these 2 things. We're trying to predict the product. So up in the corner here, I want to recognize, okay, when aluminum is ionic, it's aluminum 3+. But when aluminum's a metal in its elemental form, what's the charge of this? Just aluminum? 0, yeah. And this is okay. Aluminum is changing forms. It's going from metallic, its elemental form, to ionic. That's fine. That's fine. That's not part of the learning objective here. We need to figure out, okay, when aluminum is in an ionic compound, what's its charges? All right. So, because this is going to help us predict what that ionic compound needs to be. So aluminum is 3+. What is chlorine usually when it's in an ionic compound, the charge? minus 1. So now do you have a better idea of what that product has to be? Yeah. What is the formula for that product? AlCl3. And ionic compounds are solid, like salt, so it's a solid. Okay. All right. So we did the hardest part, and that was identifying the reactants and products. Okay, identifying the What a lot of students want to do for predicting the product, they just want to smash these two things together and write AlCl2. That's just what they want to do. All right. But in this case, AlCl2 implies that chlorine or aluminum is a +2 cation, which doesn't happen. So we need to actually predict with proper charges using chapter 2 stuff what is present. Yeah. Okay, that's a great question. So remember when I asked, okay, so I asked you, what is the charge of this aluminum? And what did we say? No. This aluminum metal, when you are interacting with like aluminum foil, it's not charged. Aluminum metal is a 0 charge. I always try to clarify myself and say when aluminum is in an ionic compound, aluminum is +3. But when you just have a hunk of aluminum, it's a neutral. It's in a charge neutral state. And that's okay. Both are allowed. All right? And so it's the same thing for chlorine. Diatomic chlorine is neutral. Both those atoms are charge neutral. But when chlorine is in an ionic compound, it's a -1. Does that make sense? Where you can have oxygen. The oxygen you and I breathe, it is charge neutral. O2 gas, just like chlorine, is charge neutral. But when oxygen is in an ionic compound like calcium oxide, it's 2-. Does that make sense? Okay, great. Or here's another example, like in molecular compounds, we can have chlorine atoms in molecular compounds too, because it's a nonmetal, right? So when chlorine is in an ionic compound, it's -1. But when chlorine is in a molecular compound, it's charge neutral, right? Okay, yeah, and so that's a common like misconception or thing that students fall for. Okay, so yeah, these two are charge neutral. This is also charge neutral, yeah.
Wait, but then how does it change from like the chlorine gas because it's CO2? How does it change from 2 to 3? How is it balanced?
It's not balanced yet. Yeah, it's not balanced yet. So all we did was identify stuff. That's it. Yeah, yeah. Oh, that's fine, it's fine. Okay, so we're not balanced yet. So how can we balance it? Yeah, so there's 2 chlorines on one side, 3 on the other side. So my best guess is to put a 3 here and a 2 there. So then you balance the chlorines. And then the tip is, I mentioned before, if you have an element that's like alone, try to balance that last so you don't screw up everything else, because then we can simply add a 2 in front of that aluminum to make all the atoms themselves balanced. All right? And so what's happening here is that these chlorine atoms that are neutral on the reactant side, they're gaining electrons when they go to the product side. We'll save that for Chem 1220 when you learn about electrochem and like how electrons are involved in chemical reactions. But for now, all you need to know is how to identify substances based upon their name, charges if necessary, if naming ionic compounds, and then adjusting those coefficients. Okay, so what kind of reaction is this? Look at our 3 up here. This is a combination reaction. Very good. All right, so we did a combination, so we're probably going to do a decomposition next. So again, names to formulas. So we have mercury 2 oxide. We heat it, and it decomposes to elemental mercury and oxygen gas. So let's identify everything. Okay, mercury 2 oxide. What kind of compound is that? Ionic. How do we know? There's a 2. Yeah, so it's telling you the charge. Exactly. All right, so mercury is Hg, and I'm trying to tell the reader that it's a Hg2+. Oxide is typically what? What charge in an ionic compound? O2-. So that's how we figure out what the formula for mercury 2 oxide is. So it looks like it's HGO. This is a solid, although I should have specified it in this question. And it decomposes. So does that mean that, is there any other reactants present? No, it's just mercury oxide. Yep. Okay, but now we need to figure out what the products are. Okay, elemental liquid mercury, what is that? HgL liquid, yep, that's it. All right. So there's one of my products. And then the other product? O2 gas, yes. Okay, perfect. So there's our skeleton structure for our balanced chemical reaction. We've identified everything. All right, so quick refresher. So the mercury that's in the ionic compound, it's ionic. So it's mercury 2+. It is a cation. But is mercury in the liquid elemental form, is that a cation? No. So what's the charge of this mercury? Neutral, 0. Yeah, is that okay? Can we do that? Yeah, we can do that. Yeah, it's fine. Or the oxygen in mercury oxide. That oxygen is in an ionic compound, so it's O2-. But is O2 gas, is that, yeah, nope, that's charge neutral, and that's fine and dandy to have, all right? This question, it's not about the electron transfer. I just want you to identify those substances. Okay, so we have the appropriate subscripts were needed, so now we just balance using coefficients. So don't change any subscripts at this point. What a lot of students will do is they'll just put a 2 there. Ooh, but if we do that, if we put a 2 in mercury oxide, yeah, then we change the charges and everything gets messed up. So don't do that to try to balance it. So instead, I'm going to put a coefficient of 2 there. So the oxygens balance and then mercury balances like that. And that's it. Okay. We just took all that time to figure out the subscripts. Don't screw it up by changing your subscripts to balance it. Only change your coefficients to balance atoms. Okay, so those are combination, decomposition. So what do you think's next? Combustion, yep, okay. Okay, so balancing a combustion reaction. So I tell you, gaseous propane undergoes complete combustion to form gaseous products. So just like in the previous reactions, yeah. I didn't need to. I didn't need to clarify. I can just say when mercury 2 oxide is heated, it converts to liquid mercury and oxygen gas. I could have said that too, and you could have still gotten the answer. It's just I needed a verb. And why not use a verb that's specific to this reaction? Yeah, so. Okay, all right, so this question, gaseous propane undergoes complete combustion to form gaseous products. So just like before, we need to identify our reactants and products, and that's always the hardest thing, right? Because I recognize, oh, I'm burning some type of fuel, but did I give you the chemical formula for it? No, I didn't, all right? I'm telling you we're burning propane, but I didn't give you the chemical formula. How do you think we can get the chemical formula? Just, you can either memorize it. Do you want to memorize it? No, so let's just draw it and then figure out what that chemical formula is. So we do have to somewhat memorize what prop means. And what does prop mean? 3, yeah. So prop means that there are 3 carbons in a row. And what's the trick with carbon atoms? It always forms 4 bonds. So the carbon on the left side has how many hydrogens attached to it? 3, yeah, because there's already a carbon bond formed, so it needs 3 additional bonds. So all of those blue lines, those are hydrogens. The middle carbon has how many hydrogens? 2, and then the last one has 3. So you can tell that this formula is C3H, how many hydrogens? 8, yeah, so that's how we get it, okay? All you need to know is carbon always makes 4 bonds. Carbon makes 4 bonds, and hydrogen, you just tack hydrogens on there. Okay, so that's how we drew the structure, we got the formula, all right, and so now we just burn it. So C3H8 is our reactant. Since we're burning it, we're also adding oxygen gas to the mix, and since this is complete combustion, our 2 products are CO2 and water. So you do need to know that about a combustion reaction, all right? Oh, and I tell you it's gaseous propane, so we can put gas there. All right. So there's our skeleton structure of our chemical reaction, where I used subscripts to identify stuff. So now it's on to atom balancing, where we just change the coefficients. And so I have a bulletproof way to balance any combustion reaction, and it will always work. And so basically, the order that you want to balance your atoms is carbon, hydrogen, and then balance oxygen last. That's the general way you do it, all right? So let's balance those carbon atoms first. So we look at our substance we're burning. We want to balance it by changing the coefficient in front of CO2. So how many CO2 molecules am I going to produce? 3, all right? So carbon, then hydrogen. So how many hydrogens am I burning? 8. There's 8 there. And so now we need to put the appropriate coefficient in front of water, but recognize that each water molecule has 2 hydrogens. So do I want to make 8 water molecules? No, we want to make only 4. Yep. Okay. So carbon and hydrogen. So do carbon, hydrogen, those are the easy steps. Now let's balance oxygen. All right? So this is how I do it, is I count up, so I'm done on the product side, right? I filled in coefficients where I need it. So what I do is I count up how many oxygen atoms do I have on my product side total. So each CO2 molecule is giving 2 oxygen atoms. So how many oxygens are coming from CO2? 6. And then how many are coming from water? 4. So there are 10 oxygen atoms on my product side. So I need to make sure that there are 10 oxygen atoms on my reactant side. So can you tell me what coefficient I need? 5, yes. And again, because it's O2, every oxygen gives 2 oxygen atoms, so we only need 5 of them. And then you can double check yourself that everything is balanced. And so that's the way you balance a combustion reaction. We have one more step if something weird happens, and that'll happen on the next slide. So I recognize that a question like this is hard to give on an exam. So that's what the next question is. It'll say something like, okay, write the balanced combustion reaction of propane, and then tell me what is the sum of all the coefficients. That's how we ask questions like that. Because if you screw up just in one place, then your sum will be wrong. But what I do want you to recognize, how we read this question, even though there's not a coefficient in front of propane, that a 1 coefficient is still implied. So do know that, all right? So if we wanted to report the sum, it would be 1 plus 5 plus 3 plus 4, and what is that? Like, I can count 6, 13, right? So like if this was on an exam, you would report the sum of 13 or something like that, okay? All right, so let's do another example. So this time we are, this is like an exam type question where it could be like numerical input. You just put a number in a box, and this would be the full question. What is the sum of all of the coefficients in the balanced equation for the combustion of methanol? So again, I didn't give you the formula, so we need to draw it. But that's okay. Methanol, meth means what? 1. So we have 1 carbon atom. Carbon always makes 4 bonds. But since this is methanol, what does that mean about one of the bonds? So they're all hydrogen except one of them is we replace with an OH group instead. So it's OH, and then there's 3 hydrogens. If it was methane, then all 4 would just be hydrogens. And so that's how we get our chemical formula. And so you'll see methanol a lot. It's a common solvent. In textbooks, you'll oftentimes see methanol, its formula written like this, CH3OH, where they're trying to tell you have this CH3 group and then this OH group, which makes it an alcohol. So they write it out like that. But you might just count up all the atoms and say, oh, this is CH4O. Whether you use either of those, it'll still balance the exact same. It's just textbooks will oftentimes write it this way where the OH is tacked on the end. So you clearly see it's an alcohol. Because if you just write this, can you tell that it's an alcohol? Not really, you can't. So that's why in textbooks you'll see it written like this. Okay, so I'm gonna use it this way where that's our reactant, CH3, OH. I didn't give you phases here, but do we need to write the phases to answer this question? No, so do you want to skip it? Yeah, so let's just get those coefficients. I already did the hard part and got the formula, all right? So since this is complete combustion, what is the other reactant? O2, and then what are my products? CO2 and water. Okay, so remember my strategy. What do we do first? Balance carbons, okay. So we balance carbons by changing the coefficient in front of CO2. So what's the coefficient in front of CO2? 1, yep, good. Okay, next we balance hydrogens. So do be careful here. How many total hydrogens are in methanol? 4, not 3, right? Because there's like, I've written hydrogens in multiple places. There are a total of 4 hydrogens. So what's the coefficient in front of water? 2. Okay, great. Okay. Then what's the next step? Oxygens. And so I still follow my exact same strategy as before. We're done with the product side. So I'll take inventory of all of the oxygens on my product side and make sure my reactant side matches. So oxygen here, 2 are coming from CO2, and then 2 are coming from water. So there's a total of 4 oxygens present. All right, so I need to make sure my reactant side also has 4 oxygens present. All right, so what a lot of students will do is recognize, oh, I need 4 oxygens, so I'm going to put a 2 in front of O2. Can you do that? No, because if you do that, how many oxygens are on my reactant side now? 5. Yeah, so that's a problem. But don't worry. This is how I approach it. Okay, so I need a total of 4 oxygen atoms on my reactant side, and the goal is here is to just adjust the coefficient on oxygen gas. We want to keep methanol as a coefficient of 1. So what I recognize is, okay, methanol is giving me 1 oxygen already. So how many oxygens need to come from O2 to make this all balanced? 3. Yep, 3. Okay, so you need to pick a coefficient that gives you 3 oxygen atoms, all right? So if I had a coefficient of 1, that gives 2 oxygen atoms. If I have a coefficient of 2, how many oxygen atoms is that? 4. So that means what's the coefficient in front of here? 1.5. What is that as a fraction? 3 halves, yeah. So my coefficient in front of O2 is 3 halves. All right, I'm almost done. All right, so those are my coefficients, but there's a problem. We don't want a fraction in our coefficients here. We want them to be whole numbers, and that's where the last step is. Number 5, if O2 has a fractional coefficient, multiply everything by 2, and then you're done. All right, that's it. Okay, so let's multiply all these coefficients by 2. So the new coefficients will be 2, 3, 2, and then 4. And then all of that, if this was an exam where you report the sum, you would just add those all up, and it's 11. All right, okay. So let's, let me show you another example where if we have oxygen present in a compound, how that would balance. So let's say we had like I'm just gonna make something up, okay? Okay, something like this. Let's pretend you did the balancing and you need this to add up to, I'm gonna make something up, 9. Okay, that you need all of the oxygens to add up to 9. What would the coefficient in front of O2 be? So same strategy. How many oxygens are coming from the compound? 2. So then how many oxygens need to come from O2? 7. So what's the coefficient in front of oxygen? 7 halves, yes. And then if you were balancing everything, you would multiply everything by 2. So that's how you approach it. Or let's do something different. What if it was like that? What if it was like that? So CH4O3, what's the coefficient in front of O2 gas? 6? 3, yeah. So 3 oxygen atoms are coming from the molecule, which means you need 6 to come from O2. But remember, it's O2. So you can think, oh, it has to be 6 halves, which is 3. Yes, it's 3. Okay, all right. Is that good? Follow the steps. Take inventory of your oxygens at the very end and just adjust O2 as necessary. Okay, so those are combustion reactions. Okay, so we did balancing, and so the hard part there is identifying your chemical formulas. So let's put our chemical formulas in our periodic table to use finally. We get to finally use it. And calculate masses of molecules that you're working with in these balanced chemical equations. So when we write a chemical equation with the molecular formulas, those formulas tell us what atoms are bonded to one another. So like a carbon atom has, a mass of 12.01 AMU. But if we had methane, which is CH4, to get the whole mass of methane, we would just sum up all of the masses of that carbon atom and 4 hydrogen atoms. So we're using the periodic table, taking inventory of all of those atoms that are actually bonded to one another, and getting the full molecular weights of those compounds. So I just want to clarify some terminology here. Methane is a molecule. It's a molecular compound. But is NaCl a molecule? No, it's not a molecular compound. NaCl is an ionic compound. All right, so if we want to use the correct terminology here, if we wanted to calculate the weight off of the periodic table for CH4, it's a molecular weight because CH4 is a molecule. We can calculate the same, masses off the periodic table for NaCl, but because NaCl is not a molecule, it's an ionic compound, technically we call it a formula weight, technically. But if you call everything a molecular weight, no one's gonna blink an eye at you. We all know what you're talking about. They're actually calculated the same, but again, I wanted to showcase that molecules versus ionic compounds, their structures are different. We name them differently. They even technically have different names for these weights, but we calculate them the exact same. We just use those periodic table masses in the unit of AMU, which stands for atomic mass unit. So let's do it. All right, let's calculate the weights of ethanol and calcium hydroxide. So ethanol is a molecule because it's we name it using molecular naming rules. You can pick up discrete ethanol particles. It's made of only carbons, hydrogens, and oxygen, so only nonmetals. So it is a molecule. So molecular weight will have a unit of AMU that we get off the periodic table. But we have a problem. I didn't tell you the chemical formula of ethanol. How do we get it? Draw it. Yeah, so let's draw it. All right, so ethanol, F means what? 2. So 2 carbons in a row. So those carbons all have 4 bonds, so we would think that they all have hydrogens attached to it, but that's ethane. So to make it ethanol, what do? Add an OH where we swap one of the hydrogens with an OH group instead. Doesn't matter where you put it, so I'm just gonna put it there. All right, so that's an OH group, while the rest of those bonds are hydrogen atoms. Right? And so then we can write the chemical formula for this. I can write the expanded version. It'll be like CH3, CH2, OH. So you can write it that way to clearly show how the carbons are bonding, or you could just write it C2, H, what is that, 5 OH. You could write that as well for ethanol, or you could just write C2H6O. Regardless of how you do it, you'll still get the same chemical, like molar mass or molecular weight. It's just, again, how we write the formula. Sometimes we can at least show a little bit of the structure through the formula. right? Regardless of what you use, you'll get the same weight for this. So let's do that. So I'm actually going to use this one down here because it clearly shows me that this molecule has 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. All right, because I want to take all of those weights off of the periodic table and add those masses up. So carbon has a weight off of the periodic table is 12.01 AMU, but there's 2 of them. So I want to multiply that number by 2. Right? Hydrogen, if you look off the periodic table, it's 1.008 AMU, but there are 6 of them. And then oxygen is 16.00 AMU, and there's 1 of them. Right? And so we want to add all of these up. So this operation is all addition. All addition. Yes, I know I did 2 times 12.01, but you could also think of that as 12.01 plus 12.01 plus 1.006 or 008 6 times. So it's actually all addition. So for addition, do we count sig figs? No. What do you do for addition? You just look at place values. So how are we going to round this number to report it? 2 decimal places. Yes, 2 decimal places, because it looks like we're limited by oxygen and carbon. All right. So the answer here is something like 40 something. Yeah, I wrote it down. 46.07 AMU. 2 decimal places, because it's addition. Yeah. So whatever the periodic table is on the exam, use those numbers. So don't just say hydrogen is 1, because you are always given periodic tables that says hydrogen is at least 1.008. So if you just write 1, you're being lazy, because we give you the full number, right? So yes, don't pre-round, okay? Yeah, especially if you're using that number in calculations. Don't be lazy. Just use the full number off of the periodic table, okay? Yeah. So that means, yes, use 12.01. Try not to use 12. Okay. All right, so, okay, so let's calculate the formula weight of calcium hydroxide. So if I say formula weight, that implies that this compound is ionic. Is calcium hydroxide ionic? Yes, it is. And that's going to help us get the chemical formula, because I didn't give it to you because I'm evil. But that's okay. This is chapter 2 review, and you did have your homework due yesterday. So hopefully you should know what calcium hydroxide is. So let's go through this step by step. Ionic compounds are made of ions, so we need to predict the charges. Calcium is what in an ionic compound? 2+. Hydroxide is what in an ionic compound? 1-, but the full thing is OH-, yes, because hydroxide's not on the periodic table. It's a polyatomic. That's one you have to memorize. So the full charge neutral ionic compound here is going to be calcium, OH, 2 of them, right? So there is my formula unit for this ionic compound. So it's the same exact strategy. Just take inventory of your atoms, add them up using periodic table masses. So we have a calcium. How many oxygens do I have? 2, yeah, because that subscript works. I'm trying to say, hey, you have 2 hydroxide particles there. So there's 2 oxygens and then 2 hydrogens. All right, so off the periodic table, did I write this down? Maybe calcium, there's 1 of them. It's 40.078 AMU. 2 oxygens, so 2 times 16.00. And then 2 hydrogens, so 2 times 1.008 AMU. Add all of that up. When you add this up, where do we round? 2 decimal places, yeah. And so my answer, oh, it's in the corner, great. So it's 74.10 AMU. Okay. If you use a different periodic table that has more decimal places, you might get different numbers. Like your rounding for sig figs might be a little bit different, but it'll be close to this. right? So that's what one formula unit of calcium hydroxide weighs, all right? So just based upon how we did this math, calcium hydroxide, the weight is like 74 AMU. Most of that mass comes from which atom? Calcium, yeah. It's like 40. It's like 40 of the mass, so it's like over half of that mass. So that's another way we can look at compounds here is through the masses of all of the elements that it's made out of. And this will be important coming up here when we do empirical formulas. So percent composition for a substance depends on what atoms are present in that chemical formula. We can calculate the percent mass of each of the elements present, all right, by dividing the masses of that element divided by the full mass of the molecule itself. So here's an example, methane, CH4. Here are the atomic masses for the individual atoms. So if I wanted the percent mass of, let's say, carbon in this molecule, you would take, first figure out the full mass of just one methane molecule. So you do what we did before and inventory all your atoms, and you'd get that the full molecule weighs something like 16 AMU, 16.04 AMU. This 2 subscript, I'm just trying to tell you, I didn't round yet, but that 2 is, I would have dropped that for rounding, but I left it there because I'm actually not done with my calculation yet. So the molecular weight for methane should have 4 sig figs, 2 decimal places, but I want to keep that too. All right. Okay, so that's the full molar or molecular weight of methane. So to get the percent mass of just the carbon atoms, we just take the mass of just the carbon from our calculation, and then we divide by that full mass that we got before, and we see that, okay, in methane, carbon constitutes almost 75% of the mass of the molecule. And we can do the same for hydrogen, but do keep in mind the subscripts there. There are 4 hydrogens present in the molecule, so 4 times the atomic mass of hydrogen divided by the full mass of the molecule. And we see that the rest there is 25%, right? So what's special? Oh, I already wrote it before my mouth said it. What's special about these 2 numbers? They add up to 100. Yeah, so once you get one, you can figure out the other one by just subtracting from 100. All right, okay. We'll use this, keep this information in our back pocket for coming up. Okay, so let's do one more. Rust. Rust, like at the bottom of your vehicle, is Fe2O3. Let's name this compound. What is it? Well, first, remember chapter 2, how we approach these. Ask yourself, is it molecular or ionic? Ionic, how do we know? There's a metal. Okay, you're answering that. Okay, so ionic naming rules. So what's the rules for ionic naming? Just name the cation, then the anion. So this is iron oxide, but there's something missing. It's not 2. But I like your enthusiasm. Yes, it's iron something oxide. How do I know? So I'm trying to tell you that we need a parentheses. We need the stock system here. How do you know you need Roman numerals? Because iron is a transition metal. It's not a charge you can easily predict, like if it was groups 1 or 2. All right, so we have to tell the reader exactly what the charge is. So we do that by knowing what oxygen is. Oxygen is always O2 minus. There's 3 of them. So the total anion charge is -6. So that means the total cation charge is +6. But there's 2 irons, so that means iron must be +3. That's it. Yep, iron 3 oxide. Chapter 2 review. All right. Okay, so iron 2 oxide, what's the formula weight for it? Did I use the right terminology? Yes, I did, because it's ionic. But again, if you said what's the molecular weight of iron 2 oxide, like, yeah, it's the same. Okay, you do it the exact same way. So we just take inventory of everything. So we have 2 irons and then 3 oxygens. So iron is one I haven't memorized yet. So 2 times 55.85. But remember, you don't need to memorize these ever, because you are always given a periodic table, always. But I promise you by the midterm, you will memorize oxygen, carbon, and hydrogen. I promise you. Yeah. You just will. So oxygen, there's 3 of them, and it's 16.00. Right, and then we just add those up. How many decimal places will my answer have? 2. Yeah, so it's 159.70 AMU, because it's all addition. Okay, so that's the weight of my full molecule, but then the last part here is, okay, what's the percent iron in the sample, or in rust? So to get percent iron, we just need to figure out, okay, how much of the sample is iron, and divide it by the full weight of the molecule. So I just take the work I did up here, just take whatever that number is. So 2 times 55.85, that's the mass of just iron, divided by the full mass we just got, 70. So I'll just work that out. So it's 111.70 AMU. That's the mass of just iron. And then 159.70 AMU times 100. And since the division, both those numbers have 5 sig figs, my answer, my percent iron will also have 5 sig figs. And I have that in the corner right there. All right, so 69.944% iron, 5 sig figs. All right, okay. So if we wanted the percent oxygen, how could we do it real easily? Subtract from 100. Yep, but you can do the work too and prove it to yourself. You'll get the same answer if you just take whatever that number is and divide by the full mass and get percent iron, percent oxygen. This will come back around here shortly. Okay, so iron oxide. This is the mass of one formula unit. When we looked at methane here, CH4, it weighs 16 AMU. Do you know, in your mind, can you imagine what an AMU, like how much an AMU is, an atomic mass unit? Do you know what that means? No, it's just, they're just letters to you, right? But if I ask you, do you know, can you imagine how much 16 grams weighs? Could you imagine kind of what that looks like? Yeah. All right, so AMU isn't a great unit for working with in lab because we are never working with just one particle, one molecule. We're always working with billions, trillions of them. So scientists use we've scaled up the amount of stuff we work with in terms of moles of substances. So a mole is just a counting number, okay? I can have one particle of something. I could have a pair of something. What does a pair mean, typically? Like P-A-I-R, pair? 2, yes. What about a dozen? What does that mean? 12, yeah. So a mole is just a counting number, just like when I say, oh, like a pair of shoes, which implies 2, a dozen eggs, 12, right? A mole just means 6.022 times 10 to the 23 of that thing. And so the reason we chemists use mole is because it's easier to actually measure things when we are working in moles of substances, because we're able to relate it to grams. So for example, do you go to the store and buy 1 egg? No, you buy eggs in dozens, right? Because it's easier that way, all right? So it's the same idea, all right? And the great thing about us kind of converting to this mole value is that everything on the periodic table stays the same. Those numbers, we use the same table. Our stoichiometry here, our coefficients, they mean the same thing. Those numbers still remain the same. It's just we've scaled everything up. Like here I say, oh, for every 1 oxygen molecule, I get 2 water molecules. But I could also say, for every 2 dozen oxygen molecules, I get 2 dozen water molecules. Or I could say, for every 1 mole of oxygen, I get 2 moles of water as we scale things up. All right, so mole, it's M-O-L-E, that's like how you spell it, but oftentimes I will abbreviate it M-O-L to save 1 whole letter. All right, so this number, you are given it on the exam. I've already posted the supplemental information. You looked at it? Did you look at it? Hopefully you did, yeah? It's been posted for a while now, but we actually do give it to you, so I'm surprised about that, okay? So you don't have to memorize it. But knowing how to use it, that's the important thing. Okay, so what's the significance for the mole? I told you, we're scaling things up Scientists, chemists were lazy and were cheap. We don't want to make a new periodic table with new numbers, right? Because if you look at carbon, carbon is 12.01. The mass of one carbon atom is 12.01 AMU, right? But if we are talking about a mole's worth of carbon, scientists don't want a new table to understand how much a mole's worth of carbon weighs. So what we're going to do is use a mole and recognize the number stays the same, but the unit changes. So from the periodic table, carbon, one carbon atom is 12.01 AMU. But if we actually have a mole's worth of carbon, so 6.022 times 10 to the 23 carbon atoms, it weighs 12.01 grams. So it's the same number, just a different unit. So water, right? We can go through water, 2 hydrogens, 1 oxygen. It weighs about 12 AMU, 1 water molecule. But if we had a mole's worth of water molecules, it weighs 18 grams per mole of those particles. So we don't have anything in lab that can measure things in AMU. We don't have an atomic mass unit machine. But we do have something that weighs things in grams. So it makes more sense for us to talk about atoms collectively in this unit of moles, which just means a very, very, very big number. All right? So that's how molecular weight and molar mass are similar but different. Molar mass, it's the same number, but molar mass is talking about the gram amount of a mole's worth of substance. Right? And that's the power of the periodic table. It tells you the average mass of one atom in AMU per that one atom, or it tells you the mass of that element in grams per mole of that atom. So let's put it all together. So just from the unit of molar mass, you can see that you can calculate it with an equation. If you know the gram amount and the mole amount, you just divide those two numbers to get grams per mole. So if I tell you that this compound, cholesterol, a 0.00105 mole sample of cholesterol has this mass, what is the molar mass of cholesterol? All right, so I have a gram amount. I give it to you in the question, and I give you a mole amount. It's in the question. So it looks like it's just plug and chug here. So to get the molar mass of cholesterol, I'll just do 0.406 grams over 0.00105 moles. I wouldn't even consider this an equation. It's just I'm looking at the units and dividing by the appropriate things to get it. All right, and so we see that cholesterol has a molar mass, so that's why I put molar mass, is 387 grams per mole, right? So if I scaled this up, if I had 1 mole of cholesterol, it'll weigh almost 400 grams, okay? All right, so if I have a mole's worth of cholesterol, it weighs 387 grams. How much does 1 molecule of cholesterol weigh? 387 AMU, yes. So that's the clever, if we're clever with our units, you can recognize periodic table. It tells us AMU per atom and gram per mole of substance. But I want to show you mathematically that it's the same thing. Yeah, question? Yes, moles of, if I have a mole's worth of cholesterol, of that molecule, then it weighs almost 400 grams. Yes, yes. Does that answer your question? Correct, yeah. So I could have a mole of eggs. I could have a mole of bicycles, but each of those bicycles has 2 tires, right? So if I have a mole of bicycles, how many moles of tires do I have? 2 moles of tires. Yes. So yeah, that relationship still works out here. All right. So yes, you guys were clever with your units. The molecular weight of 1 cholesterol molecule is 387 AMU, but I want to prove it to you using dimensional analysis and units. So we just calculated molar mass, so that's grams per mole. But this question, I'm asking you, okay, what is the weight in AMU per molecule? right? So remember dimensional analysis. We can convert stuff that's on the top and the bottom, right? Can you convert gram to AMU? Is that something you can do? Given the expressions, the constants that I gave you up there, could you convert grams to AMU? Yes, because I give you the conversion factor. Can you convert moles to molecules? Yes, with the conversion I give you. So I can convert the top and the bottom, but what's the trick with dimensional analysis? You can convert the top and the bottom, but you just have to do them one at a time. So let's do that. So this is kind of just like practice in chapter 1 stuff, where I'm converting grams per mole to AMU per molecule. I'm converting the top and the bottom just one at a time. So I'm gonna rewrite that molar mass I just got. So 387 grams is 1 mole of compound. Right, what do you want to convert first, top or bottom? Bottom, yay, someone who's weird, different. Okay, so let's convert moles to molecules. So I'm gonna use this second conversion that says 1 mole equals 6.022 times 10 to the 23 particles, but in this case, it's molecules. Molecules of this cholesterol thing. So where's that 6.022 gonna go, top or bottom? Bottom, yeah. 1 mole goes up top. 6.022 goes on the bottom. 23 molecules of cholesterol, okay? So we see those units cancel, mole cancel, because we're doing the bottom one first because we're weird. So we've converted moles to molecules. Let's convert grams to AMU. So we're going to use that first conversion here. All right. So where is AMU going to go in my next fraction? The top. Yep. 1 AMU goes on the top, where the 1.66, I don't feel like writing all those numbers, times 10 to the negative 24 grams is on the bottom, because that allows me to cancel grams, and I'm left with the units AMU per molecule. Okay, so in your calculator, I want you to put 387 divided by 6.022. Hopefully you've learned how to use the exponential key by now. So it's E23 divided by 1.66, E negative 24. Put that in your calculator and tell me what you get. You should already know what you get, but like I want to prove it to you. That the periodic table, it's both in AMU per atom and gram per mole. Do you get 387? Yay! Isn't that satisfying? Kind of satisfying, right? Okay, so it works both ways. So obviously you don't need to do this conversion every time you want to switch from like molecule masses in AMU to mole masses in grams. You don't need to do that. I just wanted to prove it to you that it does in fact work. Okay. Okay. All right, so let's do another one. Let's calculate the weight of 2-propanol. How do we do that? Draw it. So propanol means what? So prop means what? 3. So 3 carbon atoms. It's an alcohol. So 2-propanol is implying that the OH group is on the second carbon atom. So I'm just going to put that OH right there. But it doesn't really matter. We'll still get the same chemical formula regardless. Because that's how I get the molar mass is, or the mass of the molecules. I need that chemical formula. And if I put the OH in the wrong place, it'll still be the same formula. So there we go. OH is on that middle carbon. And the rest of the atoms have hydrogen, so each of those carbons have 4 bonds. All right, so there's my structure. Let's get the formula. I'm just going to add up all the atoms because I'm just weighing it here. So I have 3 carbons. How many hydrogens do I have total? 8, and then 1 oxygen. All right, and then apply those appropriate atomic masses. So 3 times 12.01. 8 times 1.008, and then plus 16. All right, so this answer, oh, it's in the corner, perfect. 60.09 AMU, so 2 decimal places, because we're limited by carbon and oxygen. Okay. Oh, wait, AMU, is that the right unit here? Yeah, I asked for molecular weight, so it's the weight of one molecule. So then what is the molar mass of 2-propanol? Do we have to do this all again? No, you just need to recognize that molar mass is a different unit. It's the unit of grams per mole. And so all you have to do is just use the same number, but a different unit. So the molar mass of 2-propanol is 60.09 grams per mole. All right. I'll be honest with you, we are going to use molar mass much more often. But if I tell you the molecular weight of something, if I tell you that like the molecular weight molecular weight of like diatomic nitrogen is 28.00 AMU, in your brain you should automatically think that, oh, nitrogen, a sample of diatomic nitrogen is also 28 grams per mole. It means the same thing, right? So we're going to be using molar mass much, much more often. And the reason is, look, the unit is grams per mole. So remember in chapter 1 where I said like cool conversion factors come from units that have fractions in them, right? Molar mass is a derived unit. So what does it mean? 60.09 grams per mole. How could we rewrite that as an equality that's useful to us? It means that the top unit gets the number. So if I have a sample of 2-propanol, 60.09 grams of propanol is equal to 1 mole of propanol, or in this, 2-propanol, whatever. All right, if I have 1 mole of 2-propanol, it's going to weigh 60 grams, right? And that's very useful to us as a quality because I can use it as a conversion factor where I can put the 60 grams on the bottom or the top, depending on how I am converting my units. You don't have to memorize, do I have to multiply or divide by molar mass? You don't have to memorize it, just cancel those units out. It's a derived unit, just like in chapter 1, okay? Because this is really the meat and potatoes of chemistry, using molar mass, converting gram amounts to mole amounts, because in lab we have balances that measure grams. Do we have any instruments that can measure mole amounts of stuff? No, we can't. So we have to be able to convert gram amounts to mole amounts. As long as we know the formulas and the weights, we can do that. So let's look at this example. Caffeine has this formula. So we could go ahead and calculate the molar mass, but we don't have to because I tell you that the molecular weight is that, 194 AMU. So what's the molar mass of caffeine? 194.19, but what's the unit? Grams per mole. So let's rewrite that as a useful equality for us. Okay, so remember how we do this. You take the number and the top unit, and you set it equal to the bottom unit with an implied 1. That's how all derived units work. So I can write an equality that says, if I have 1 mole of caffeine, so that's the bottom unit, I'm just going to call it caffeine, so CAF, equals 194.19 grams. Right? So this means if I have 6.022 times 10 to the 23 molecules of caffeine, it's going to weigh 194 grams. Cool. So this first question, I give you a gram amount of sample, and I want you to convert it to a mole amount. So the strategy here is start with what's given in your question. Let's look at the conversion factor that's given here. And it's just a chapter 1 question, right? We just want to cancel the units. So where's that 194 going to go? On the bottom, yep. As long as you understand molar mass is a conversion factor. The gram amount equals 1 mole of compound. I'm going to put the 194 on the bottom, all right, is 1 mole of caffeine. And we get a number like a little amount, 4.9 times 10 to the negative 4 moles of caffeine. All right. It's a little mole amount, but it's still like billions and trillions of molecules. Okay, so that's grams to moles. We can use the same equality to convert from moles to grams. Just cancel out those appropriate units. So let's remember here's my equality. So if I start with a mole amount and I get into a gram amount, where am I going to put the 194? On top this time, yep, because 1 mole goes on the bottom, and then 194.19 grams goes up top. Right? And so this sample weighs 35 grams. 2 sig figs because the mole amount has 2 sig figs, okay, of caffeine. Okay. All right, let's keep going. So if we look at this kind of roadmap, we just kind of played around with this first stop between grams and moles using molar mass. Sometimes you multiply, sometimes you divide by that number. Again, it depends on the direction, the unit that you start with. Just cancel the units. So once we're in a mole amount, we can actually use Avogadro's number as a conversion factor too. Avogadro's number says that 1 mole equals a ton of particles, just like we can say 1 dozen of something equals 12 of that object. So we can go from like mole amount of things to individual particles by using Avogadro's number of that substance. So if I have a mole amount of caffeine molecules and I use Avogadro's number, it will convert to individual molecules of that substance. All right, so we're going to use Avogadro's number as a conversion. We're still going to use the molar mass, okay? So how many caffeine molecules are present in like 7 grams of sample? So we're still going to use molar mass here. Where am I going to put the 194? On the bottom. 194.19 grams is on the bottom, and then 1 mole of caffeine on top. This puts me in the unit of moles of caffeine. But I don't want to stop there. I want to keep going to molecules. So this next step, I use Avogadro's number. But again, we need to cancel units. So where am I going to put the big number, on the top or the bottom? Top, because 1 mole is going on the bottom. So for every 1 mole of caffeine, I have 6.022 times 10 to the 23 caffeine molecules. All right, and that gives me some answer. There's a lot. 2.16 times 10 to the 22 caffeine molecules. All right, there's my answer. Okay. Okay. So that's like, so yeah. So each, if we counted every single caffeine molecule, remember caffeine has this formula. Those are the atoms that are actually bonded together. If we counted each of those particles, we would get that 7 gram mass. So this next question is kind of similar. We're actually just working off what we just calculated, but instead of stopping at molecules of caffeine, I want you to tell me how many carbon atoms are present in that same sample. Okay, so if I told you I have 8 bicycles in my garage, how many tires are also in my garage? 16, yeah, because we recognize that 1 bicycle has 2 tires. So you know how many caffeine particles are in the garage. How many carbon atoms are on each caffeine molecule? 8. How did you get 8? It's in the formula. Yep. So how do we get this next one? If we continue on with our previous question, how do we get number of carbon atoms? Multiply this number by 8. And the reason is we're actually, in the back of our heads, we're coming up with a new conversion factor. It's for every 1 caffeine molecule, there are 8 carbon atoms. All right. So that's the new conversion that I'm using. So instead of rewriting everything, I'm just going to copy all the work I had before. Okay, so this is how we would start it. Okay, it's the same exact work. You turn grams to moles of caffeine, moles to molecules of caffeine, and then turn molecules to individual carbon atoms based upon the chemical formula. So the last step here that's missing is for every 1 caffeine molecule, there are 8 carbon atoms. And so then we're just multiplying that last number by 8, so it's 1.72 times 10 to the 23 carbon atoms. There we go. Okay. So that one's not bad. Turning gram amount of this molecule to moles, to molecules, to individual atoms given that chemical formula. So this next question, a little bit harder, and it's backwards. But it's actually the same question as this carbon atom one, but backwards. But there's some places to go wrong. So I give you hydrogen atoms, but I want you, so I'm giving you hydrogen atoms of this caffeine sample. Right, this caffeine sample has this many hydrogen atoms. I want you to tell me, well, okay, if you know how many hydrogen atoms you have, how much does it actually weigh, the caffeine weigh? So what a lot of students will do with this question is they'll see, oh, hydrogen atoms. They'll convert that to moles of hydrogen, and then they'll multiply by 1.008 grams. But if you do that, you're telling me the weight of what? Just the hydrogen. But is that what the question's asking? No, it wants the mass of caffeine. So we need to figure out how many molecules of caffeine are present, how many moles of caffeine are present, given this amount of hydrogen. So how can we relate caffeine to hydrogen here? Is it 8? Is it 8 hydrogens? No, it's 10 hydrogens, yeah. So for every 1 caffeine molecule, there are 10 hydrogen atoms. I'll tell you a funny story. Actually, I'll finish the question and then I'll tell the funny story. Okay, so so we know the relationship between hydrogen and caffeine, so we're going to use that to figure out how many caffeine molecules I have given this hydrogen. So where am I going to put the 10? On the bottom, yep. So 10 H's on the bottom, 1 caffeine molecule. Okay? So at this point, I could multiply this by AMU, but I want it in grams. So I'm going to convert this to moles first. That's easier for me. So I'm going to use Avogadro's number. But this time, where am I putting the 6.022? On the top or the bottom? This time it goes on the bottom, yeah, because I'm actually in molecules and I want to convert to full-blown moles. So 1 mole goes on the top, and then 6.022 times 10 to the 23 goes on the bottom. So now I'm in moles of caffeine. So this is now where I can use the molar mass of caffeine. So for every 1 mole of caffeine, it weighs 194.19 grams. All right, and so this full sample will weigh 138 grams. All right, okay. Yeah, so the step here is we got to scale those hydrogen atoms to how many molecules of that thing that we actually have. Okay, I'll tell you the funny story. First time I taught 1210, I think I used a very similar question like this when I taught that class. And I think I had them do it, but like this example, like 10, I had them calculate from hydrogen atoms how much the sample weighed. And so they recognized, oh, okay, yeah, 10 hydrogen atoms, 1 caffeine molecule. So we did a bunch of examples using caffeine and hydrogen. And then it came time for the exam, right? And so on the exam, I gave a question just like this one, okay? But I didn't ask it for hydrogen. I asked it for nitrogen. I gave them how many nitrogen atoms they had, and I asked them, how much weight of caffeine do you have? 50% of the class used the same 1 = 10 conversion. Yeah, and you're laughing, right? Maybe because I did the same example over and over and over, and it was always 1 = 10. But then I recognized, I guess I just wasn't, relating it back to the chemical formula. So yes, I changed it to nitrogen on the exam, and 50% of the class still used one molecule equals 10. I don't think they understood what that conversion meant. So that's the funny story. Don't make that mistake. Actually look at the chemical formula. Okay, so we have 5 minutes here. So I'll just start this next part of the chapter where I bring back empirical formula and the relevance of empirical formula. I promised it was coming back to percent composition that we just talked about. So let's review empirical formula. It's the simplest ratio. All right, So let's look at these examples again. I give you moleculars. Let's get the empirical and the multiplier. So what's the empirical formula of hydrazine? NH2. What's the multiplier? 2. Benzene, CH. What's the multiplier? 6. Acetylene, also CH, but the multiplier is 2. And then H2O, but the multiplier is 1. So in that example, the molecular and empirical formula are the same. Okay, so this is why empirical formulas are important. So we just learned about percent composition, okay? So we calculated the percent composition of iron and oxygen and rust, right? It was something like 69% of iron, of rust is iron, of that mass is iron, and then like 39% of it is oxygen. So from those percentages, you can actually figure out what is the ratio between the iron atoms and the oxygen atoms. But the thing is that percent composition experiments, they can only tell you the empirical formula. That's it. It can only tell you the simplest ratio. So in order to get the molecular formula, you actually need the empirical formula and the multiplier to get that molecular formula. So percent composition data only tells us the empirical formula. That's why it's called empirical, which means by experiment. Experiments only tell us empirical formulas. We need an additional piece of information to get a molecular formula, and that information is the molar mass of the full molecule. Full molecule. Okay? So I want you to write this down. There's 4 minutes left. So write this down. The steps to determining an empirical formula. These work every single time. They work every single time. So just memorize the strategy here. But it's not that bad. There's a lot of words written here, but on the next slide, I think it's better if we just kind of put it to use and do this strategy. So we can determine an empirical formula when given percent composition data of the elements, right? So for example, I'll put this in red here so it's easier to see. If I tell you that you have a sample that is 61% carbon, 39% hydrogen by mass, the idea here is to turn percents into gram amounts that we can actually work with. You want to assume that you have 100 grams of sample. Because if you do that, then those percentages become gram amounts. And then we can work with gram amounts, right? If you have a gram amount of carbon, we can convert that to moles. If we have a gram amount of hydrogen, we can convert that to moles, right? So the strategy here is convert percentages to gram amounts. So if I have 61% carbon, how many grams of carbon are you going to start with? Assume we have 100 grams of sample. 61 grams of carbon. And then how much hydrogen do I have? 39 grams of hydrogen, all right? So just turn those percentages into gram amounts. Because then once you're in gram amounts, we can convert those gram amounts to moles of each element. How do we convert from grams to moles? Molar mass of the respective elements, all right? All right, so then once we have gram amounts to mole amounts, we're one step closer to getting that mole ratio. All right, so I'm going to set the next question up here. All right, so we have a compound. It contains carbon, hydrogen, and oxygen by mass percentages. So I have the strategy written here. We want to go from percentages to gram amounts, grams to moles, and then that mole ratio. So how are we going to first start this? We want to turn those percentages into grams. So what am I going to write? 68.54 grams of carbon, 8.63 grams of hydrogen, and then 22.83 grams of oxygen. So our next step is we need to convert those gram amounts to moles. Yeah, how do we do that? Periodic table, all right? So we just divide by those respective molar masses. All right, the molar mass of carbon is 12-ish, but it's 12.01 grams is 1 mole of carbon. For hydrogen, it's 1.008 grams. It's 1 mole of hydrogen. So you see that I'm dividing everything here. And then oxygen, it's 16. So 16 grams is going to go on the bottom, 1 mole of oxygen up top. All right, so I got that started for you. So we'll just leave out, we'll pick up here on Thursday. But maybe you can figure out the empirical formula of this question yourself. Did the heavy lifting for you.